If huge electrical power is to be distributed over long distances, then it has to be done at medium voltage, which could be 11 kV or 33 kV. If the voltage is more than 33 kV, it is classified as high voltage, which is 8V. So 8V is usually used in transmission system. So in this situation here, where we are distributing at medium voltage, especially 11 kV, by so doing, the problem of high voltage drop is eradicated, and in addition, the difficulty in installation, that is the problem of difficulty in installation, as well as high cost of installation, all those problems are alleviated as well. So we see, by making use of one example, we will illustrate how to do power distribution system at medium voltage, especially at 11 kV. So we have an example to illustrate that. Now, moving on with the example on MV electrical power distribution system. The example is as follows. A factory measuring 1 kilometer by half kilometer, located where there is no electrical grid, is to be powered using diesel generators, given that the power requirement of the factory is 1.3 MVA at 400 volts line to line, 230.9 volts line to neutral at 50 Hz frequency. The 1.3 MVA is spread over 4 electrical load centers as follows. Load center A 480 kVA, load center B 480 kVA, load center C 170 kVA, load center D 170 kVA. Now the question is, design the power distribution system for the factory. The interpretation of the question is that the designer or the consulting engineer will need to state the method or the concept to be used in doing the power distribution system, that is, in carrying out the distribution system. And also, he or she must size or state the sizes of all the equipment and the sizes of devices that will be involved in the power distribution system. So that is, and then we move on to how to find solution to the problem. Now, solving the problem, what one needs to consider first is, what is the concept to use or to be used in carrying out the power distribution within the factory, which is measuring 1 kilometer by half kilometer. So the concept here is that we are generating voltage, making use of low voltage generators. We synchronize their output and step up the 400 volt output to 11 kV. That's why we are having a step up transformer here. Then from the step up transformer, we go into the 11 kV panel, which is an MV panel. It's an MV panel, a medium voltage panel, which is 11 kV. Then from there, we go to the 4 load centers, A, B, C, D. So which now we can be called transformer substations in this situation. So, and the line of supply is a kind of ring. So the ring is closed by this RMU with the third terminal having no connection. Moving on, still on the design. In designing, apart from knowing the concept to use, then all the sizes of all items involved in the design must be stated or calculated, And that is why the generators we are having here, each of them is rated 600 kVA at 400 volts line to line, and at 50 Hz frequency. Now, the output of the three generators are synchronized. This panel is synchronizing panel, and it's also performing the work of or the function of load shedding. So the number of generators that will be switched on at a time depends on the load demand from this transformer substation or from the loads. So it may even happen that it's only one generator that will be operating if the load that is or the power consumption is what one generator can cope with. So that is the situation. That is why we have this line, all this line, the line C9, C9. They are generator signaling line or signal lines. The synchronizing panel signals to the generator that should be switched on or you want to be shut down, as the case may be or as the situation may be. So that is the function of this synchronizing slash load shedding panel. Now we have to make sure that the output of the generators 600 times 3 is actually more than 1.3 MVA, which is the power requirement for the factory. If you multiply 600 by 3, you get 1.8 MVA, which is quite good. And then we make sure that the circuit breaker we are using, this is 2000 ampere triple phase with neutral MCCB model case circuit breaker. And then we also have 100 at the output of we have 800 at the output of each generator. So from there, from the synchronizing panel, we move to the step up transformer, which is 1.6 MVA. So, and also the 1.6 MVA should be more than 1.3 MVA, which is the factory load requirement or the power requirement. So that's why we are having 1.6 MVA. That is the transformer that, or step up transformer, that is suitable for this situation. So we have this the 400 volts on the primary side and 11 kilovolts or 11,000 volts on the secondary side. This is medium voltage, and this is the low voltage, which is 400. This is 11 kV. Then from there we go to we move into the voltage enters the medium voltage panel. This is it, which is 11 kV panel. So with the circuit breakers inside, and then from there we have the rings that the ring line that feeds the transformer substations A, B, C, D. All right. Now, what is another thing that is important, or what is important again, is that we need to size all the cables. We've been able to size the step up transformer, and then we've chosen the generators, their sizes. Then we have the RMU with time. I'm going to state the rating of the RMU. Each RMU has 630 amps switch at each of the network terminals. This is one network terminal, this is another network terminal, and this is the load terminals. What is coming into them, what is coming into each of them is 11 kV. So each of them is stepping 11 kV down to 400 volts. So 11 kV volt to 400 volts. And this is feeder pillar 1, feeder pillar 2, feeder pillar 3, and feeder pillar 4. And we are going to state their current rating later. Now, this is the RMU that is closing the ring. It has no connection at the load terminal. So if you want to isolate, you want to separate the two lines, we can switch off this terminal and this terminal, and the ring is broken, and that is that. Now we move on to another stage. This MCCB circuit breaker 800 amp triple phase with neutral is protecting this generator. It makes sure that much of the power that is more than the power that the generator can supply is not required, or it's not drawn from the generator. That is protecting the generator. So 800 amp, this one is also protecting this. And the 2000 amp triple phase with neutral circuit breaker, MCCB circuit breaker, is protecting this transformer. The transformer can actually supply more than 2000 ampere, but what we really need is not up to 2000 ampere. So, but 2000 ampere is, 2000 ampere triple phase with neutral circuit breaker MCCB is protecting the transformer. So the actual current, the actual load current is less than 2000 ampere. So, and this one is vacuum circuit breaker. So let me write it there. Vacuum circuit breaker. Vacuum circuit breaker. VCB. This is also VCB. So the three of them, this, and this, they are all vacuum circuit breaker. Vacuum, because the extinguishing medium inside is vacuum. So that's why it is called vacuum circuit breaker. Alright? So, as I said, that all items involved in the power distribution system must be sized. So it means we've known the sizes of the generator. We need to calculate the size of the current rating rather of the circuit of the cables, LV cable. Then here this is MV cable, and then even all these ones, they are MV cable, are the same size. So for that purpose, three-phase apparent power S in kVA is equal to √3 IL VL. IL is the line current, while VL is line voltage, and it's also equal to 3 times I phase V phase. That is 3 times phase current and phase voltage. So we can use any of the two formulas to calculate whatever we want, whether we want to calculate the current or voltage. So for instance, the load requirement is which is 1.3 MVA. If we put 1.3 MVA here, we can easily calculate the current, since we know that if the phase voltage is given as 230.9 volts, so we can calculate the phase current, which is used in sizing in knowing the load current. So for instance here, 600 kVA, if you put it here, we calculate the current that is flowing, the phase current of the generator, and that's why we are able to select 800 amp circuit breaker. So MCCB in this case. So, and then when we add up the output of the three generators, we have to select the circuit breaker that we make sure that excessive current is not drawn from the generator. So this is 2000 ampere. So this is the standard one that is available. So we need to consider the availability of circuit breakers as well. So that is what this formula is useful for. It's also useful for this one. Neglecting losses. The power on the secondary side, which is the apparent power S, on the secondary side is the same as the apparent power S on the primary side. So since this one is star, it's very easy to use this formula to calculate the magnitude of the current flowing here, and from there we make use of a manufacturer's catalog of cables. So the manufacturer that is trusted, like in my own situation, I'm using the cable broker from Nexans. So, and that is how I came about all these calculations and these figures. So these are vacuum circuit breakers. These are MCC, this model case circuit breaker. Alright, then from here I'm defining what each of these one stands for. I is in ampere, V is in volts, not in kilovolts. And also this one, we can if we know the phase current, we can calculate the line current using this formula. I line is equal to √3 times I phase. It's actually I phase. I phase, not I phase. And V line, which is the line voltage, is √3. V line is equal to √3 V phase. That is 3 times the phase voltage, and √3 is 1.7321 approximately. And the P1 that we are talking about here is load shedding slash synchronizing panel. So it decides how many generators are to be switched on. Alright, and P2, which is MV 11 kV panel, this one is 11 kV panel, and is the one housing the 3 vacuum circuit breakers. So we have a FE, feeder pillar. This is a feeder pillar 2, 3 and 4. Okay, attached to the 4 transformer stations. Alright, the RMU is the ring main unit, this one, and each terminal has its own switch. Each of the network terminals, this one network terminal, it has its own switch, which is rated 630 ampere, triple phase 630, and we have a load terminal where we have 200 amps TP, that's triple phase circuit breaker, to supply the voltage to the transformer, each of the transformers we have here. Alright, and we move on. For the purpose of clarification, these are the major calculations that led to the choice of the items here. For instance, factory total load current. This is the total power requirement. We divide by 3 and we divide everything by 230.9. This 230.9 is is 400, that is the line voltage, divided by root 3. So if we divide 400 by root 3, that is 400 over 1.7321. That is what you will get. You get 230.9. All right. So that's 230.9. So similarly, generator phase current also is this, because we have this one per phase. This is what we have. The neutral current is not this. It has to be calculated separately if you want, but that is not what we are concerned with now. Then step-up transformer, the line current here is this. Yes, the current is low, yet we need to choose this size of vacuum circuit breaker, 400 ampere, because it's readily available. The 200 amp is not usually readily available, and it is the size of this vacuum circuit, the current rating of this vacuum circuit breaker, that determines the choice of this cable, which is going to be 300 SLPE armored cable, as we are going to see later. So that is the situation. The step-up current transformer at the LV side is this. So you can cross-check as you want, and that's how it is for now. The calculation continues. RMU, ring main unit, with 630 amp TP, that's triple phase, at each of the two network terminals, and 200 amp TP circuit breaker at the load terminal. G is the generator, so that just use G to denote generator. The three generators are equal in size, and then feeder pillar 1 is equal to feeder pillar 2 is equal to 800 amp TPN. So because there must be neutral there, the voltage has been stepped down to 400 volts. Then feeder pillar 3 is equal to feeder pillar 4, so which is 320 amp triple phase with neutral. Then we have the step down transformer TX1, which is the same as TX2, 500 kVA each, since the load requirement at load center A is 480, so it's reasonable to choose a 500 kVA transformer. The same thing at B. So at load center C, the power requirement there is 170 kVA, so it's reasonable to select a 200 kVA transformer and move on. These are the cable sizes. They are all LV cables, LV low voltage cables, except C3, C4, C5, and C6, which are 11 kV cables. All of them, all this one, they are 11 kV cables. 11 kV. Alright? And they are just 3 in number, because we have a delta connection here, not star. It's only when we have star that we have 4 sets of cables, but in this case where we have delta connection, it's only 3 sets of cables. So, and we move on to the final stage. And these are the sizes of the panels. This panel is P1. P1 is a synchronizing / load shedding panel, 2000 ampere TPN, MCCB panel, that's the rating. Alright, with 3 number 800 amp TPN MCCB incomers, and 1 number 2000 ampere triple phase with neutral MCCB outgoing. These are the incomers. There are MCCB incomers, and this is the only outgoing that we have there. Then P2, this panel P2 is 400 amp TPN 11 kV panel. Alright, so this one is a LV panel. It's a low voltage panel. Okay, LV panel. It's low voltage panel. While this one is this one is 11 kV panel with one number 400 amp TP PCB incomer. So this is the only incomer here, and it's a PCB. The circuit breaker is a vacuum circuit breaker, and then it has two number 400 amp TP PCB outgoings. This one, there is no neutral here since it is delta side of the transformer. So PCB means vacuum circuit breaker. That's at 11 kV. We use it at 11 kV. And the no connection here means this NC here means no connection. Finally, I hope that the video is found useful. If it is so, please consider subscribing to my channel, JK Solutions. Thanks for watching.